Concrete is the most widely used construction material on Earth, but it has one stubborn weakness: it cracks. Over time, those cracks allow water, air, salts, and pollutants to seep inside, corroding steel reinforcement and shortening a structure's life. To tackle this, researchers have developed self-healing concrete. It's not a single miracle product, but a family of technologies designed to let concrete repair its own small cracks with little or no human intervention. This video explores where these ideas came from, how the different systems work, where they are being used, how they behave in wet climates, and the real-world advantages, costs, and limitations that come with them. One of the most famous modern versions, often called bioconcrete, was developed in the Netherlands by microbiologist Henk M. Jonkers at Delft University of Technology, TU Delft. His work, which began around 2006, helped turn the science fiction idea of living concrete into a serious field of engineering research. It also highlights that self-healing in concrete can be chemical, mineral, or biological in nature. But before we get started, please consider hitting the like button and subscribing to my channel before the end of this video. It only takes a second to do, and it really helps support my work. Thanks for watching and helping me reach 1,000 subscribers. Ready? Let's begin. The bacteria-based system most people associate with self-healing concrete traces back to Henk Jonkers. Starting in the mid-2000s, Jonkers investigated how certain bacteria could survive inside concrete and produce minerals that seal cracks. By roughly 2009 to 2010, the concept of bacteria-infused self-healing concrete had been clearly demonstrated, and Jonkers' work later gained international attention, including recognition connected to the European Inventor Award in 2015. Interestingly, researchers have also found that ancient Roman concrete exhibited a form of natural self-healing through mineral reactions involving lime clasts. However, that is a rediscovered historical material system, not the modern bacteria-based technology developed in Delft. Self-healing concrete typically relies on two broad mechanisms: autogenous healing and autonomous systems such as bacteria-based or capsule-based approaches. Autogenous healing is the built-in ability of ordinary concrete to heal very small cracks under the right conditions. When water enters fine cracks, unreacted cement particles can continue to hydrate, and calcium compounds can react with carbon dioxide to form calcium carbonate, which helps seal the crack. This process is limited to tiny cracks, usually below about 0.2–0.3 millimeters, and depends on the presence of moisture and leftover reactive material in the concrete. The more advanced Jonkers-style bioconcrete adds a biological twist. Tiny capsules or porous carriers containing bacillus bacteria and a nutrient source, often calcium lactate, are mixed into the concrete. In the highly alkaline environment of hardened concrete, these bacteria can remain dormant for years or even decades. When a crack forms and water and oxygen enter, the bacteria become active, consume the nutrients, and produce limestone, calcium carbonate, that gradually fills and seals the crack. Besides sealing the crack, this process can locally consume oxygen and help slow the corrosion of embedded steel reinforcement. Other experimental systems use microcapsules or small channels to release polymer or mineral glue when cracks open, but these approaches remain more niche and research-focused. Despite the buzz, self-healing concrete is not yet a standard off-the-shelf global product. It is mainly used in specialized mixes and pilot projects. Research linked to Jonkers and related spin-offs has produced a self-healing concrete for new construction, a self-healing repair mortar, and a liquid repair treatment for existing structures. Trials and demonstration projects have appeared in parts of Europe and elsewhere in structures such as bridges, tunnels, precast panels, and water-retaining infrastructure. However, large-scale adoption is still limited by cost, compatibility with conventional admixtures, and the need for long-term performance validation under real service conditions. Water is not the enemy here. It is actually a trigger for healing. Both autogenous and bacteria-based systems rely on moisture to drive chemical reactions or activate bacterial activity. In climates with high humidity, rainfall, condensation, or splash exposure, microcrack healing can be more effective because water is regularly available without continuously washing healing agents away. In marine or very wet environments, the ability of self-healing concrete to seal fine cracks can help limit the ingress of aggressive ions such as chlorides. Still, if the environment is extremely harsh or cracks are too large, healing may be incomplete, and conventional durability problems like reinforcement corrosion can still occur. Practical crack width limits typically fall around 0.5 to 1 millimeter for many autonomous systems, and smaller for purely autogenous healing. The main appeal of self-healing concrete is reduced maintenance. By automatically sealing small cracks, it can lower the frequency of inspections, patching, and sealing operations over a structure's life. This contributes to longer service life and improved durability, since fewer open cracks mean less water, carbon dioxide, and chloride penetration. There are also sustainability benefits. Structures that last longer require fewer repairs, replacements, and associated cement production, which can reduce life cycle carbon emissions. Another advantage is that healing is passive. It is triggered by normal environmental exposure, especially water entering cracks, without the need for sensors, power, or active intervention. The development of self-healing repair mortars and liquids also extends the concept beyond new construction to the rehabilitation of existing structures. The biggest hurdle today is its cost. Conventional structural concrete in many markets may cost on the order of $100 to $200 per cubic meter, while some research-scale bacteria-based self-healing concretes have been cited at figures around $6,000 per cubic meter. That represents an enormous premium, reflecting specialized bacteria production and small-scale manufacturing rather than mature industrial pricing. Self-healing systems also have crack size limits. They are not designed to fix wide structural cracks caused by major overloads, design errors, or ground movement. Adding capsules, carriers, or special agents can affect workability and mechanical properties, requiring careful mix design. Long-term durability over many decades, especially under repeated cracking and harsh exposures, still needs further field validation. Finally, the lack of widely adopted design standards and codes makes mainstream acceptance slower. Beyond full concrete mixes, Jonker's work has included self-healing repair mortars and liquid treatment systems for cracked surfaces. These are intended mainly for sealing fine cracks in existing structures, rather than replacing large volumes of damaged concrete. Even these products generally work best for crack widths of about 1 millimeter or less, meaning major structural damage still requires traditional repair methods such as removal, replacement, or epoxy injection. Self-healing concrete is a fascinating blend of chemistry, materials science, and even microbiology. Pioneered in its modern biological form by Henk Jonkers, it includes both natural chemical healing in ordinary concrete and advanced systems using bacteria or encapsulated agents. Moisture, far from being purely harmful, is essential to its healing action, making humid environments potentially favorable for sealing small cracks. However, the technology is still specialized, expensive, and best suited to micro cracks, not major structural failures. Its biggest promise lies in extending service life, reducing maintenance, and improving durability and sustainability over the long term. For now, self-healing concrete is less a universal replacement for standard concrete and more a high-tech durability upgrade. It's gradually moving from research labs and pilot projects toward broader real-world use. So, is this high-tech concrete worth it? Leave me a comment, then check out some of my other videos. Don't forget to hit the like button and help me reach 1,000 subscribers. Thanks for watching until the end, and we'll see you at the next one. Take care. Bye for now.